Hey again, guys. So here we are for part 2. Thank you for joining me, tolerating a second round. You'll notice my symbol for 2. It looks more information theoretic than the symbol for 1 I used last time. That's because we're going to move into some more interesting information theoretic ideas and how these spectral intuitions we built up last time can be applied to really get at some deeper questions. So this is just recycled to get us back in the right mode, and or perhaps a superposition of correct modes. We're thinking, of course, about processes as having these intrinsic modes of how they churn probability density, and information is flowing kind of according to these modes, that it's kind of rattling around and decaying and oozing. And if you want to at some point know something about your process, you not only let everything ooze, but you then take a measurement of your system and see kind of what output you have or something like that. So again, I was suggesting that the spectral methods are kind of formalizing our intuition in some sense. And this also is familiar. Last time we talked a little bit about dynamic stuff, correlation functions, power spectra, and we didn't get to some of this other stuff that I'd had up here last time, which were the more information theoretic ideas here. So from any presentation, we could get all the stuff we did last time, which was kind of a neat thing, that if you just figure out any way to write down a machine that reproduces the statistics of the process, you can immediately get these pieces here that are quite interesting. And now we're moving on to, I don't just want to observe my system, but I want to understand how information is flowing, what kind of the information transduction is in my system. And so I'm going to have to get a little more sophisticated, but really it's the same sort of tools. We're using the mixed state presentation, for example, for some of these other things. But that's basically because, as I was suggesting last time, if you have a question, you need to figure out what is the stuff happening, like in what sort of space is that? Like when I say that I need to crank the process forward, what dynamic am I talking about? And oftentimes for information theoretic quantities, we're talking about probability distributions, and so we need something like a mixed state presentation that evolves probability densities or probability distributions. So we'll get to talk about this today, and so I'm excited about that. And then kind of one other step beyond that, just kind of along our progression of things we can do if we want to ask questions, for example, about something about the causal states of a system. That's kind of by definition question about the epsilon machine. So in that case, you have the way to pose your question in terms of the distributions over the epsilon machine, and then we can get things like synchronization information. So I think most of the information quantities that we've talked about in this class, if there's others, let me know so then I can analyze them. Or you can. That's fine with me too. Okay, so just a little bit of review what we covered. Basically last time, there's some talk of functions of operators, overview of spectral decomposition, and I'm kind of glad we got some of that introduced, because then I think we'll be using even more of that today. And of course, we talked about specific general results, including dynamics, correlation functions, power spectra. So, for example, the power spectrum for the even process we found is just something about these projection operators for the transition matrix of the even process, and then there was some kind of interesting dividing by eigenvalues, and but everything that you really need for most of the questions is contained in little scalar packets that are usually questions that come down to throwing a bra and a ket onto the projection operators with maybe some other stuff. So there were, for the even process, there were two modes. There was the eigenvalue of 1 and of -0.5, and so those came into play for the in the power spectrum, and you could simplify that, and you got a pretty looking curve, which was nice. It's really good to have that. And in general, if our alphabet's just zeros and ones, and your transition matrix is diagonalizable, then you have something like this, like for the even process. So I guess since you guys have had a chance to have this all soak in for the last 2 days, I want to talk a little more about consequences of even just having it written down this way. So take a look at this form, and we're saying that this is the most general form of a power spectra that you can have if your alphabet is 0 and 1 and your transition matrix is something diagonalizable. So I can also write down more general things, but it's just harder to see through. And so we start to see kind of limitations on what's possible of power spectra if they can be defined by a finite state hidden Markov model. And of course, it can be non-unifilar or whatever. But so some of these consequences is that the number of states for any presentation of a process puts an upper bound on the number of peaks in the power spectrum. So you can kind of see that from the number of states that a hidden Markov model has. So then it basically says the dimension of the matrix, right? If you have a 3-state model, you have like a 3x3 transition matrix, right? Well, there's only 3 eigenvalues that you can have, and one of them is unity. So there's only like 2 kind of interesting ones you can have. And so when you add up these terms, you can only have some two humps in your power spectrum. So it's kind of an interesting perspective in various ways. Conversely, the number of peaks in a power spectrum, let's say we don't know what our process is and we just do some measurement and we get a power spectrum. Well, that tells us something kind of nice, just kind of from a quick glance at the power spectrum. It'll give us a lower bound on the number of states of any presentation. So it's basically saying if you're looking at some power spectrum and it has 5 bumps, that means the minimal even non-unifilar machine has at least 5 states. So it's kind of interesting structural information you can get just immediately from looking at it. But they can be very loose bounds. But for example, the simple non-unifilar source that I think you guys have talked about a little bit, right? So it's kind of this interesting process that its minimal unifilar representation, its epsilon machine is infinite states. So you think, gosh, maybe it'd have a very complicated power spectrum if it's an infinite state process. But we know that it can be represented by a 2-state non-unifilar machine. And we actually know this is the minimal non-unifilar representation has 2 states. And so this puts limitations on the power spectrum, right? And indeed, the power spectrum is something simple. It has, if you consider this like kind of a continuous function, it's like 1 peak per 2 pi. And it's also interesting, like compared to the even process. If you remember, the even process had exactly 0 power at some points, right? Like there were forbidden energies, if you will, because you couldn't get anything like 0, 1, 0, 1, 0, 1. The SNS basically has all allowed frequencies. It clearly has a different structure. Instead of being peaked like this, it's kind of peaked on the opposite end, kind of more high frequency components, if you will. And I mean, this is also a little particular to a choice of the to the parameters P and Q, but it's also kind of interesting to sweep through and see what happens. However you sweep through it, you know that the structure is pretty limited. Okay, on the other hand, like I was suggesting, you do some measurements. You do X-ray diffraction. You shoot an X-ray at a crystal, and you get this out. So I made this claim yesterday or Tuesday that a diffraction pattern is it's just the power spectrum of the structure factors. So I claim that's true, and it's especially obvious when you have disorder along one dimension, which happens a lot for technologically interesting materials like silicon carbide, many layer graphene, multi-layer graphene, whatever you want to call it. Lots of stuff that's actually technologically very interesting. But I kind of would stand by this being pretty generally true, that even in higher dimension, the diffraction pattern it's a power spectrum of the structure factors. So we look at this, we do some measurement, and we get all these peaks. So how many states, if the process is spitting out an alphabet of structure factors, what's the minimal number of states for this crystal? I mean, it's at least 1, 2, 3, 4. I can't count that high. It's quite a few. And similarly, so this is from claimed to be a measurement from a typical zeolite beta sample, something. And this is some X-ray diffraction done from like multi-layer graphene on silicon carbide. So it's like people are interested in this stuff, and they kind of model it. And they usually use like very big computers to like fit parameters and stuff. But they're not looking at this and saying, oh, interesting, the information processing being done by this crystal has at least 10 states, but we could be saying that. Okay, so what do we expect, for example, from the random XOR process? If you guys were still sticking with me at the end of last time, you probably remember I made this claim. So this is random XOR process. Here's basically what it is. I don't have any coins, but had I some coins, I would flip one, and I would flip another. And then, so that's kind of random, and random again. And then what's the next symbol that I'm going to spit out at you? It's the XOR operation of the last two, so exclusive OR. If I have a 0 and a 1, then I give a 1. If I have a 1 and a 0, I give a 1. If it's a 1 and a 1, I give a 0, 0, 0, I give a 0, right? And then I step over here, and I'm trying to get rich, so I ask for more coins, and flip, flip, do it again, flip, flip, do it again. So there's something here. And I claimed that there's 0 pairwise correlation in that process, which maybe seems plausible because, you kind of need two things to happen, and then the third kind of depends on that. So it's kind of like a three-way interaction, at least. This is the kind of a presentation for that process where, let's say you start here, you flip a coin, half a chance that you get a 1, half a chance that you get a 0, and when you flip the next coin, it's kind of independent of that. Half a chance that you get a 0 for this guy would give 0, 0, and half a chance for this guy that you get a 1 would give 1, 1. Alternatively, it was half a chance that you go to the 0, 1 state or to the 1, 0 state here. And depending on what the two symbols were together, If it's 0, 1, or 1, 0, then you emit a 1. And if it were 0, 0, or 1, 1, you emit a 0, right? So it's like logic gates almost. I mean, it's kind of a boring computation. It's just one XOR gate. But it's a little more sophisticated than some of the other things we've been talking about. And this is the power spectrum. Right? What? So white noise, really? So this is really, if you measured the power spectrum of this system, you would be led to believe that this system is just pure noise, pure white noise. And so this is an example of kind of what Jim's coined as regularities unseen, randomness observed, right? I mean, really randomness observed. So we need, so here's just kind of a little motivation to transcend what we did last time. It's great that we have the tools to get things like power spectrum, but if we limit ourselves to pairwise correlations, we're going to miss a lot. And in fact, I'd suggest that as we look at more sophisticated processes, that kind of the decisions that are made depend on more factors, then less and less of the information processing is going to be done in pairwise correlations. In fact, we kind of have a hypothesis that the fraction of information processing done in pairwise correlations goes to 0 as you get kind of complex, interesting behavior. Yet people don't really measure much other than power spectrum sometimes. So what are we going to do about this? Must be something, right? I mean, we want to understand how the brain works, how we interact, right? All these things about information transduction. How does information move? So not just, did I see a 0 here and a 0, 1 here, but what happened, what was being computed during that time? And so we need some more sophisticated probes of structure, which I'd say there's something like measures of information transduction that they're saying how information is being processed in the system. And this is just what I was saying earlier, especially as things become more complex, we really need to be aware of how to take into account higher order correlations. So towards that end, we'll just do a quick review of some definitions from last time. If you guys want to stop me on any of it, please do. Eigenvalues for a square matrix, standard definition of that is what we're used to doing to find eigenvalues is you take the determinant of some variable lambda times the identity minus the matrix, and you find where that determinant is 0, right? So any complex number that satisfies that is an eigenvalue of your square matrix. And then I was wanting to talk about things like projection operators. There was some suggestions that we could use other sorts of things, but if you bear with me, for the projection operators, they're defined as, there can be more motivation if you want to talk about it later on, but basically the residue of this resolvent thing, which contained all these spectral information, basically as this complex variable z kind of approaches the eigenvalue. And if your matrix was diagonalizable, you get something like this. And with simpler and simpler matrices, you get simpler and simpler expressions. The projection operators, in general, they're mutually orthogonal. So they live in these different spaces. If you try to slam them together, they'll kind of annihilate unless they're the same sort of object. And for a stochastic matrix, and when I say stochastic matrix, I mean like a transition matrix where probability is conserved. So all rows sum to unity in our case. Some people define matrices so that the columns sum to 1, but if you like that, you can just take transposes of everything. But for these stochastic matrices, we talked about how all the eigenvalues lie on or within the unit circle. And the eigenvalue of unity, it's guaranteed to be there, and it's guaranteed to be there with the algebraic multiplicity equal to the geometric multiplicity. And moreover, if you only have one attractor, then there's just algebraic multiplicity of 1, in which case the projection operator associated with unity is just this thing, which is saying that in every column, sorry, for every row is just the stationary distribution. So you have stationary distribution, stationary distribution, stationary distribution, if you only have one attractor. This basically says no matter where you start, no matter what your initial distribution is, if you evolve time forward ad infinitum, you would go to the one unique stationary distribution. So okay, so we're all good with this. Then we'll go ahead and say one other thing I want to mention. I don't think I gave the projection operators kind of their fair due last time. And I got a chance to think a little bit more about the motivation, why we're using these versus some other sorts of things. So just a few reasons real quick. So these projection operators, like these sorts of things here, I'd argue they're important kind of from a structural point of view. If you're trying to understand, for example, different modes of decay, the amplitudes. So this was like for the autocorrelation function, the modes of decay were all basically eigenvalues to some power. So like decaying exponential type of thing. And there could be as many as there are eigenvalues of the system. And the amplitudes of those are determined primarily by the projection operator. So if you want to be able to isolate the modes of decay, for example, this is something you want to look at. It's also, as you'll see, really useful for if modes are misbehaving. You can just kind of grab them, pull them out of our equations, and they're kind of already isolated. And so, for example, oftentimes in physics, we run into the problem of we're doing these calculations, like infinity and minus infinity, right? And that's often because you have, it's not everything's infinite, but you have some stuff that kind of wanted to blow up, but it didn't matter anyway. So it would have been really nice if we could have just pulled that stuff out to begin with. And this is often what the projection operators allow us to do. It's like we see something it's misbehaving, it's not good for anything anyway, and so you can kind of formally pull it out, and you avoid infinities, minus infinities types of things. I'm not giving you the form yet for what this sum is. So I'm saying the past future mutual information is just some sum over the eigenvalues of W is the transition matrix of the mixed state presentation. But I don't want to spoil the spoil the fun. So to be seen. Predictions. Write down your predictions. One last thing. I find, well, second to last thing maybe, but I find this pretty interesting is that the degeneracy of eigenvalues, there's like a big deal about it, like especially in quantum mechanics, if you have degenerate energies or not. And in quantum mechanics, like your Hamiltonian is always diagonalizable. So it's like, why do we need to worry about that? There's actually a really an interesting opportunity that if you redid perturbation theory with projection operators, you don't have to distinguish between degenerate and non-degenerate eigenvalues. They don't give you any trouble. So the same thing's true with our work here. We don't have to worry about it. So that's kind of nice. And they play nicely with non-diagonalizability, and I think they're going to be pretty good when we go to infinite state stuff. So I promised we'd talk about information quantities. You guys are familiar with the length L entropy rates, right? So I think sometimes we called them like the entropy rate approximates, or the idea being that you have some process. If you just considered the entropy of single symbol statistics, for example, that would be like h mu of 1. Or if you allow yourself to look at length 2 words, and then you kind of see now what's the kind of entropy look like of my system, that'd be like h mu of 2. And as you allow yourself to look at longer and longer words, you're able to pick up on kind of more correlation that can be there until as kind of L goes to infinity, you get the true randomness of the process. It's like, even though I've considered all correlations of all order, there's still some intrinsic randomness, which would just be what we normally call H mu. But for these H mu of L, I don't like calling them entropy rate approximates, because we're not approximating them. We know them exactly, so I'd call them something like the myopic entropy rate or something like that. But however you like it, if it's defined as the difference between the block entropy at L and the block entropy for one word length less than that, well, what we really mean by this is we're expecting that things are, if things are kind of stationary, that's how we get our probabilities, right? So kind of if we're not conditioning on anything else, we're kind of secretly conditioning on things being in the stationary distribution. For example, if you had measured something even in the very distant past, your distribution will evolve towards a stationary distribution. So it's a reasonable thing to do, and just being a little more explicit than we usually are, that this is the entropy of, this is the random variable associated with this word from 0 to L minus 1. And given that we start in the stationary distribution, and so then you can interpret this as well. So we have, right, okay. This is just splitting up the word from 0 to L minus 1 is the L minus 1 symbol and everything before it, right? So not much going on there. But then since these two pieces are the same, we can then kind of reorder it as this myopic entropy rate is really, it's the block entropy for XL minus 1 given basically all of the blocks kind of one less than that. And so here's the trick. Did you guys talk about this when you were talking about mixed state? Okay, so you did. This R is a state of the mixed state distribution, right? So for the mixed state process. So a mixed state is a distribution over the original states of your process. And so when we're saying the entropy of kind of the next symbol given a bunch of past ones, we can also just say the entropy of the next symbol given that we've kind of kept track of how the probability density has spread out due to observing all these words. So this is my my kind of quick summary from here to here. We could add a lot of steps there, but I'm glad you guys motivated and talked about it in the mixed state lecture. And now we're given that the initial state, and again, mixed states are distributions, the initial state of the mixed state presentation is the stationary distribution. So given that you start in the state corresponding to the stationary distribution, and there are probability distributions induced by observed words, you kind of trickle down the transient structure of the mixed state transients, and then you observe what's the entropy of the next symbol. And that's not much new there. So sorry, this isn't as cleaned up as I'd like it to be here, but just some kind of stuff about mixed states. If you guys forgot, there's some set of states that will use this R for the set of the mixed states. So these are all of the states that you can get if you start at the stationary distribution and you observe words. Then what distributions can be induced by starting in that stationary distribution and observing words. And so again, each of these states are distributions over the states of the original presentation. We start we want to start at the stationary distribution, so we do that because that's what the entropy rate formula told us to do in the last slide. We use this as a start state because that's what allows us to calculate this, right? And just a few other things that will pop up so we know what they are. This start distribution over the mixed state presentation, it's saying start at this state, the first one, which corresponds to starting in the stationary distribution, right? So if you see something like this, it is kind of in the space of the, this is like the length of the number of mixed states, and we're saying start at the first one. Reasonable enough. And then the transition matrix, which I'll call W for the mixed state presentation. So it's also a presentation of the process. Probability is also conserved for it. So it also obeys all of the properties that we talked about for stochastic transition matrices. It typically has a larger number of states than the original presentation. So we just need to distinguish, like when I use the one here, it's kind of whatever the appropriate length vector is. That's all ones. And pi sub w, to distinguish it from the stationary distribution over the original presentation, it's the stationary distribution over the mixed state presentation, right? Okay, so we're synced up? Perfect. All right, so we talked about getting here. And this is how to make things look like linear algebra. So this doesn't look like linear algebra, and I'm going to try to make it to look like linear algebra, because then we can do linear algebra, and that's easy, kind of. So when we're saying the entropy of this thing given this stuff, we have to, one thing we can do is we can sum over all of the mixed states. Then it's if you're given these things, well, okay, well, what's the probability that you're in a particular mixed state? And then given that you're there, so given that you're in a particular mixed state, then what's the kind of like entropy of leaving that state kind of thing is this. Now what do we do? How do we make this look more like linear algebra?
But probability should be something like a power of a transition matrix.
Yeah, perfect, exactly. So that's exactly what needs to happen. Is we start at the start state, we crank forward, and we then kind of do a measurement of, how probable is it that we're actually there. So you're exactly right. So this is this probability. We start at the start state. The distribution, all of the weight is at that stationary distribution. We crank forward the appropriate dynamic, which is the mixed state dynamic. And then we measure the how much of the state is here. So I think this should actually be a delta sub eta, by which I mean it's like the delta sub pi, but it's just basically you pick out that one state and you say, like, it's a 0, 0, 0, 0, 1 at the mixed state that I'm interested in, 0, 0, 0, right? So I apologize, that should be a delta sub eta, but you have the intuition already, so that's perfect. So we start here, we crank forward, and then we kind of like apply this measurement, how much of this stuff is in this state. So that's this probability. And then we kind of just expand this entropy to say entropies are things like p log p's. So, and we know how to do probabilities as things like this, which look like linear algebra. So we express the entropy as a p log p, where the probability is, what are we doing? We start at some state eta. So given that we start at some mixed state eta, so that's where we start. And we want to just immediately measure basically probability of seeing some symbol. So you kind of measure that symbol there. So then this is the probability of, and it's very much like probabilities as we usually kind of define it. You have some distribution, transition on a particular word, and then you kind of close with the one ket, right? So it's the typical sort of thing. We can kind of interpret it as part of this more general setting now. But it's PYP, summing over all the words. And now at this point, these are all basically algebraic pieces. There's row vectors, there's matrices, there's column vectors, and we can kind of move summations around until we're satisfied. So we massage a little bit, and how do we decide what to move where? Well, one thing is, what we're really interested in is L dependence, right? None of this has L dependence. It just looks nasty. So if I called it something cute, it wouldn't look nasty anymore. So I'm going to put all of that here, and there's no L dependence there. And I'm going to call it something like this. And you can actually kind of interpret this as just the entropy of making transitions, which is basically what we were doing. That for all the different mixed states you can be in, basically what's the entropy of leaving those different states. So so when it's like this, now it looks really simple, right? It's just we start at the stationary, at the first state, we turn the crank, we let probability density trickle through, and if there's loops, it kind of turns around. And then after some amount of time, we apply the measurement and say how much entropy is coming out right now of this system. And we apply that. Okay. And this thing is that stuff. But it's not L dependent. So you can just measure it once and be done with it. Figure out what it is. All right, well, and then if the transition matrix of the mixed state presentation is diagonalizable, then doing powers of that, one way you could write it, if you wanted, you could say that it's some function of the matrix that's just basically some power of it. So it's kind of like something doing powers of all the eigenvalues, summing over all the eigenvalues, and you have the projection operators associated with them. Move the sum over here if you want. And also if it's diagonalizable, then your projection operator is that. Well, if we put that back into the myopic entropy rate formula here, then we go from, already this is like a great time saver from one alternative that was done for a long time is if you're looking at the entropy rate at length L, you have to consider all the words that can get you out there, which is terrible. So many. So this is already a lot better than that, saying that we're just taking some power of a transition matrix, but then if we can find the projection operators and eigenvalues, we can even go kind of a step simpler and just say, well, this is really just powers of some scalars, the eigenvalues, and these are just some constant scalars that we can calculate, again, kind of once and for all for any process you want. And it could even be in terms of a parameterized process. Most of the examples we have today aren't parameterized, but if you want, you could do this for like the parameterized even process or a parameterized model of your brain or whatever. And so this is actually really neat because what happened a lot is we're interested in how we learn about a system, how information gain happens with longer blocks. And so oftentimes work would be done and then these things would be numerically plotted out. But now we can calculate exactly what the decay is going to be. And it turns out that the decay of this h mu of L function is just some sum of decaying exponentials. If your matrix is diagonalizable. If not, we also know what that is. It's just a little hairier to write down. So let me just do an example real quick. So for the even process, so we've been looking at the even process, like the power spectrum, stuff like that. If we did the mixed state presentation, which I think you guys probably did already in the mixed state lecture, there turn out to be 4 states. This is 2/3, 1/3 is a stationary distribution, right? And then if you, again, there's triangles and squares. This is the even triangle process, but same old even process. If you see a triangle or a 1, and you keep seeing it, you keep rattling around in the transients. So as long as you have only ever seen 1s, you don't really know what your causal state is. If you see a 0 or a square in this case, then for sure you're in this case, right? Because this is the only way to move from a 0 in the original presentation is a 0 here. 1, 1, 1, 1, 0, 0, 1, 1, 0, right? Okay, so then we can just write down what the transition matrix is, and remember this is symbol agnostic, so it doesn't matter if it's 0s or 1s or triangles or squares. It's just marginalizing over all of the observed symbols and just saying how does probability density flow if I just let time evolve. And I want to find the eigenvalues because we found that we want to find the eigenvalues. So I take the determinant of lambda I minus that thing w, and you kind of factor it, and you see that, of course, the eigenvalue unity was there, and you also get minus 1/2. We expected that because we already got that for these guys, for this recurrent part. The part that we didn't have earlier was the eigenvalues of plus or minus 1 over square root of 2. And just to get a rough idea of where that lies, so all of these, recall, all of these happen to be on the real line. It didn't have to be that way. There's lots of processes where there's eigenvalues all over the unit circle, but this one happens to all be on the real line. But since some of them are negative, that kind of is like having some complex component almost, because it has like an angle of pi. So there is something periodic going on there, period 2, and leaky, period 2. So you kind of have leakiness here and leakiness here with kind of different magnitudes of leakiness. And this is just what we said that this thing means is starting in this state. And we can calculate all the projection operators, and if we just apply, starting from the start state, it's like just taking the first row of all the projection operators. Those are the only things that really matter for our calculation. And kind of interesting, we find that the minus 1/2 projection operator doesn't contribute at all to our measurements of h mu of L. Does anyone know why? So when we just found the eigenvalues of the recurrent structure, the eigenvalues were 1 and minus 1/2. So there's something about this recurrent structure that, at least for the eigenvalue of minus 1/2, kind of once you're there, you've kind of already done all your learning. So it doesn't contribute to reducing your entropy rate. So there's some hint of that, and that kind of thing pops up, and I think there's kind of more results that we could generate and say about when things contribute and when they don't. But of course, the rattling around and the transients definitely do contribute, and the eigenvalue with unity corresponds to the asymptotic entropy rate, so that ought to be something non-zero unless you have a deterministic process. And then we just calculate. This is basically just the entropy of leaving each of the mixed states, right? So kind of try to keep this picture in mind. Something, 1 and 0. And that is like there's some entropy associated with leaving each of these. And if you're in this state, you kind of have half-half probability of where you go, so entropy of 1 bit. And if you're here, there's no entropy of transition. You're just going back there, right? So we just calculate that once and for all. And again, if we could even do it for a parameterized even process if we wanted, and we just get some ket that doesn't change in time. But then what we do is we see how the distribution changes over the states, and then we pick out basically if you're this much in this state and this much in this state, well, there's this much entropy associated with being in that state, and so that's how time gets involved here. So from this expression we can evaluate for the even process, and there's some hints of the eigenvalues popping up that are exponentiated, and there's other stuff here. We can just change the way that looks so that for even L and for odd L, it kind of seems like there's different behavior if you're even or odd. So what does that look like? It looks like this, and you can kind of see this sort of even odd sort of behavior of how the entropy rate changes. And we also, I mean, we've seen this before, but we didn't know before that the way that it decays is just determined by these two eigenvalues. So now we know that. And now we know generally for processes that can be described by a finite number of states, we know that all of those processes decay as some sum of decaying exponentials. And we know what's decaying, it's the eigenvalues. And so there's a lot of kind of structural information that we're gaining by having taken this spectral perspective. So are there any questions at this point? All right, then one thing that I think is fun to do is to look at how do we calculate excess entropy now? Because this is, at least in this form, looking rather intractable as the infinite sum over the stuff that was pretty hard to get even to estimate before. But of course now we have, we know what this is, and it's something like a sum of powers of decaying exponentials. And you can kind of, if you cross your fingers, think that, well, if we're doing an infinite sum over decaying exponentials, that's kind of like geometric progression, right? Maybe. So if that were true, that'd be great. We get to this line by we're excluding the eigenvalue of 1, which was associated with this guy. So if you wanted, you could put more steps to first include that, and then you subtract that piece. And we also are subtracting all the eigenvalues on the unit circle. We don't have to. If we included them, they will excuse themselves. They so it's just kind of saving yourself some work by noticing that, oh, these components aren't going to do anything. And since we kind of spectrally decomposed everything, we're just pull out those parts, and then we don't have to do that part of the calculation. But okay, we still have this infinite sum, but now all the L dependence is here. This is just some scalar now, right? So you guys know where we're headed at this point. We just rearrange until all the L dependence is over here. This is, this is something we can definitely do. This is just the infinite sum from 0 to infinity of lambda to the L. It's like really just the most simple geometric progression you can get. You get 1 over 1 minus lambda. And how many of these terms do we have? Well, it depends on the number of states of your process. So for the even process, there were 4. Well, not even 4, because the eigenvalue of 1 didn't count. Which is good, because had we done 1 minus 1, this thing would have blown up, right? Which is kind of what I was suggesting at the beginning, is if we just look at things like this, you're maybe thinking that things could potentially be infinite. Like if h mu is finite, you do an infinite sum, there's an infinite amount of stuff, but it's stuff that didn't matter. So kind of in having done this and being able to pull out the W1 operator, we end up with this nice form here, right? So we've done this infinite sum. We get this really neat form, and so now we also know what excess entropy even can be like, right? So not just a calculation for it, which it's nice to have this closed form expression for it, but it limits the way that excess entropy can be, at least if your matrix is diagonalizable. And again, if it's not, then we have other formulas for that.
So you mentioned earlier that the eigenvalues can be complex valued?
Yeah.
And the formula here, this way it's written, makes it kind of look like you could end up getting a complex sum for your excess entropy.
But the complex eigenvalues always occur in complex conjugate pairs, and the projection operators are also, I think, complex conjugates of each other or something like that. They conspire to make things real.
But they cancel out.
Yeah.
Because up here it has this like 1 over 1 minus lambda.
Yeah, because you're going to have a contribution from 1 over 1 minus lambda and the 1 over 1 minus lambda star, and also the way that the scalar here is structured, they end up just giving you something like 2 times the real part,
okay.
Something like that. But it is interesting kind of how those contribute, because if you think of what the complex eigenvalues are doing, they're kind of like cycles, but if they're magnitude less than 1, they're like these leaky cycles. And so the type of information that they give to the system is kind of a unique sort. So this was for diagonalizable W, and when I came up with this, I was excited, but I was like, man, what about the general case? And also, I kind of was working through examples, and sometimes it was hard to find the projection operators, and I didn't want to. So I was, I've told these guys before, I was in and out, and the hamburger was so good, I got inspired, and I like figured out, and I wrote on the back of like the placemat, this thing. And so this is for any transition matrix W. It can be non-diagonalizable, and we can kind of briefly run through this derivation here. But the nice things here is that the only projection operator I need to calculate is W1, which if you have just a single attractor, that's just the stationary distribution in every row, right? So it turns out that in terms of this thing that at the end of the day is looking a lot like a resolvent evaluated at z equals 1, and I haven't quite said what Q is yet, but it turns out that if you're happy with taking matrix inverses, then this is it, and it's really really nice. Again, I think the eigenvalue case is still really nice, and that gives a structural insight of what's happening, kind of in the different spaces, how the information is being processed. But I still am pretty excited about this and related results. So basically, if we just stick with the powers of the matrix, so you have like W to the L minus 1 here, and H mu, that's just associated with the W1 projection operator. So we're taking the difference of these, and what's new in this line? Not much. We're just changing the index, so it's starting at 0. That's just an L. So from this line to this line, I think is was kind of one of the tricks for me to be able to do this. And what it comes down to is here I have powers of L and just minus some W1. And here I'm subtracting out the W before taking the powers of L, which seems illegal, except that I know that W does have this structure of projection operators, and W1 is one of those. And since it's a stochastic matrix, the W1 component is guaranteed to have algebraic multiplicity equal to the geometric multiplicity. And so if I think of what the powers of W look like in terms of projection operators, I can, and powers of 1 are just 1. So what I end up with is powers of W to the L. It's just W1 plus basically like powers of other stuff. So even when I'm exponentiating W, there's secretly W1 lying there and other stuff associated with other modes. So if I'm subtracting W1, even if it's powers, I can just directly subtract off the W1 part. And when I take powers of W, since the projection operators annihilate each other, that's exactly what was needed to say that W to the L minus W1 is the same as subtract W1 to start with and then take powers of L. The only weird thing here is if L is 0, then you kind of end up with something funny. And so we just consider that as, for the case that L is 0, you have another W1 laying there. But so then once we realize that, we just define this thing as it's just some other matrix. So it's the transition matrix minus the stationary distribution from each row. So we'll call that Q. I don't know, just why not? So we call it Q. And so now we have powers of some matrix, Q, and something that doesn't depend on L. And since we're summing over it, the Kronecker delta just pulls out just one piece, which happens to be equal to H mu. Because if you start at the start state and you take it forward with W1, that takes you to the stationary distribution. And the stationary distribution, if you're in the stationary distribution and you observe the entropy, you're at the asymptotic entropy rate, H mu. Right? Okay, and then also this Q to the L here, I've only taken out the W1 operator. So I might think that I'm not allowed to do the kind of infinite sum of it, because it could still have eigenvalues on the unit circle. If all of the eigenvalues were of magnitude less than 1, then I am if all the eigenvalues are magnitude less than 1, then I'm guaranteed that this kind of infinite sum is equal to like the resolvent looking thing. And so I think about this, and again, these perfect periodicities are associated with no entropy, so we can kind of, for the moment, subtract them out, and we'll call Q minus the periodic stuff extra squiggly Q. It's a little squirrely because we kind of threw it off balance, and we just carry through our operation with that. And then if you do the inverse operation, it turns out you can show that this thing is actually equal to the thing had you just left them in there. So kind of weird trick, but at the end of the day, we have this really great simple expression, this infinite sum over this H mu of L, which looked difficult. We found some expression for H mu of L, and then when we did the infinite sum was even easier than the thing that we started with. And this has been a recurring theme. Like we saw that with the power spectra, like with the autocorrelation functions, we got some expression. It was okay. It was in terms of powers of eigenvalues. And then when you do the infinite sum, you just get this really neat expression. So I love taking infinite sums now. So we can do this with all the other complexity measures. I'm not going to run through the derivations because they're you've basically seen them. They're all the same, except there's slightly different bras and slightly different kets, and all the things that happens in the middle, it's exactly the same, almost. So I'll just say, for example, that we have these expressions in general. The excess entropy is this thing that we showed. And then, man, these other things like synchronization information, transient information, they look a lot like each other. And we didn't know that because when these quantities were derived, they were derived to address specific questions of different types of information. So it's both scary that all of these things that we thought were very different, they all have pretty much the same fundamental pieces, and all of the questions we know how to ask turn out to just being like throwing on different bras and kets. And actually, for these three, it's not even a different bra, it's just here a different type of entropy, but that's still just associated with different mixed states. And here, same bra and ket, it just happens to be that the transient information, we're squaring this resolvent evaluated at z equals 1. So man, it's weird. It also it gives a lot of insight into how these things are related in new ways, and it also suggests new questions to ask. Like, well, if I have a -1 and -2 there, and those were interesting, what about -3 or something like that? Or we never defined anything beyond the synchronization information that had a -2. So what happens if we do that? Like, is that interesting? Also, I think something that that I have been somewhat dissatisfied with in these measures is that they do, like the excess entropy, it is the past-future mutual information. So that is a very specific question, and it captures all of the correlations. So it's a very powerful question. But at the same time, if we want to understand, right, we want to viscerally understand the modes of information transduction, I don't think of a scalar when I think of understanding that question. So to me, this also suggests, well, shoot, this whole thing looked a lot like a resolvent. What if I threw in a z there? Then it would be the resolvent. And it would even be not just it's not just suggestive, but that actually means something, because that's actually that would actually be the z transform of those entropy rate, the myopic entropy rate. So that would actually tell us, it would be like a transform of how entropy is produced through different correlations in the system, right? So so we can do that, and I'm just throwing in a e to the I omega onto this piece here, right? And I don't think this is exactly the quantity we'll want to consider necessarily. In fact, I'm just taking the real part here. I want the real and imaginary part at least, because then I really have the z transform evaluated along the unit circle. Or maybe I don't know why I'm limiting myself to kind of this radius of 1, except that I can visualize things nicely. And what am I visualizing? I'm visualizing frequencies. So it's different frequencies, and it's telling me something about information at different frequencies. So it's something about how my process is organized, how is the information distributed, and how is the information transduced. This is the frequency decomposition of information transduction, basically. And so there's a lot of exciting directions to go with this. Kind of now that we have it in these sort of forms, we could also do very similar sorts of manipulations for each of these. And so we have these now. We have our complexity measures. We have our scalar complexity measures. We can start to interpret now, like, what does it mean to have functional forms of them? Like, there's this whole open space. Also being able now to hopefully address infinite state processes with rigor and insight. There's a lot of exciting opportunities. So one other thing I'd like to point out here. So this is for the even process, right? We plotted something kind of similar for the even process. There's a power spectrum, right? Same frequency scale. Something was going to 0 though for that. And here, actually, I don't really understand what it means to have negative information, but here there's negative information. there's some zero crossing at some frequency. And if you evaluate this excess entropy spectrum at a frequency of omega equals 0, which is z equals 1, then of course you get the excess entropy of it's something like 0.9 something for the even process. So this point here is the thing that we couldn't calculate before in closed form. Now we can, and we have its tails, whatever that they mean, at different frequencies. And again, also at this pi and negative pi, we had zero correlation, zero pairwise correlation coming through when we did the power spectrum, but it is showing that there is information transduction that is done at that frequency. So when you look at a process, if you just are observing the symbols that come out of it, and you aren't like modeling beyond that, then you'd say, there's no pairwise correlation here. It's not doing anything interesting at that frequency, but actually it is transducing information at that frequency. And the shape of this is different than the shape of the power spectrum. So there's, I think, a lot of interesting lessons to be learned. So yeah, beyond that, here's like some various stuff we got for the even process. I kind of beat this example to death now. So hopefully you guys will have some good, fun, much better ones for your projects. There's like I said, a lot of opportunity to be had. So if you guys have any questions, that's all I have.